Hello friends, welcome back in this video session of free convection or natural convection. My name is Mr. S. Vikumba, Assistant Professor, Sharath Institute of Technology, College of Engineering, Gedra, Ichalkaranji. In previous video lecture, we have studied what is free convection or natural convection, few examples of free convection and numerical based on this. So we will continue with numerical. So numerical number 2. A hot rectangular plate 5 cm by 3 cm maintained at 200 degrees centigrade is exposed to still air at 30 degrees centigrade. Calculate the percentage increase in convective heat transfer rate if smaller side of plate is held vertical than bigger side. Neglect ITG of thickness, right? So use empirical correlation as Nusselt number is equal to 0.59, Grashoff's into Prandtl raised to 0.25 and properties of air at 115. What is this 115? Mean film temperature, that is 200 plus 30 divided by 2. Density 0.91, Cp 1.009 kilojoule per kg Kelvin, mu is equal to 22.65 into 10 raised to minus 6 and K is 0.0331, right? So first bigger side L is equal to 5 centimeter. So here if L 5 centimeter is vertical, then Grashoff's number is equal to rho square G beta delta T L cube divided by mu square. So on putting appropriate values, Grashoff's number is equal to 8.67 into 10 raised to 5. So here Prandtl number is not given, but all the values are given. In previous example, Prandtl value was directly given. So Prandtl value is equal to mu Cp upon K. Mu value is given, Cp value is given, K value is given. So Prandtl number is equal to 0.69. So after getting Grashoff's number and Prandtl's number, use empirical correlation. Nusselt number is equal to 0.59, Grashoff's into Prandtl raised to 0.25 and Nusselt number is equal to 16.41. Once the Nusselt number is known to us, find out H value, right? So Nusselt number is equal to HL upon K and the value of H is 10.86 watt per meter square Kelvin, and use this value of H in this equation. Q is equal to HA delta T. H value is 10.86, just we had calculated. Area is 0.05 into 0.03 as it is rectangular, and 2 into 200 into 30, that is both temperature difference is considered. 2 into 200 into 30, 200 minus 30. So Q is equal to 5.54 watt. This is heat transfer rate from bigger side. If heat transfer takes place from lower side, that is L is equal to 3 centimeter, its characteristic length will change and Grashoff's number will not be changed here, that is 1.87 into 10 raised to 5. So Nusselt number is equal to 0.59, Grashoff's into Prandtl's. So Nusselt number is equal to 11.18. So Nusselt number is equal to HSL upon K and Nusselt number is equal to, H is equal to 12.33 watt per meter square, and find out Q is equal to HSA delta T, which is here 6.28. So increase in heat transfer rate is equal to 6.28 minus 5.554 divided by 5.54 into 100, which is 13.5%. So by 13.5% heat will transfer when smaller side or bigger side is vertically kept. So Reynolds analogy. In previous forced convection also we had studied Reynolds analogy. Reynolds analogy is the relationship between CF and H, that is heat transfer by convection between plate surface and fluid for laminar flow over flat plate. From Newton's law of viscosity, we have shear stress in laminar flow in the normal direction is given as Ts tau s is equal to mu dV upon dy, that is dy is equal to mu dV upon tau s. Let's say it's equation number 1. Now heat flow along y direction is given by Fourier's law. Q is equal to minus Ka dt upon dy. Let's say it's equation number 2. Now from Reynolds analogy, Prandtl number is equal to mu Cp upon K. Now assuming Prandtl number is equal to 1, we will get K is equal to, as Prandtl number is equal to 1, mu Cp is equal to K. Now on substitution in equation 2 and 3, we get Q is equal to minus mu Cp A dt upon dy. That is Q is equal to minus mu Cp A dt upon mu dv into tau s. That is minus Cp A dt upon dv into tau s. Let's say equation number 4. Now applying boundary condition. Now at plate surface V is equal to 0, T is equal to Ts. For second boundary condition, when V is equal to V infinity on outer edge, T is equal to T infinity. Now integrating and substituting boundary condition, we will get Q upon Cp A tau s. Integrating from 0 to V infinity, dV is equal to minus integration from Ts to T infinity dt. And after solving this, we will get Q upon A Ts minus T infinity is equal to tau s Cp upon V infinity. And skin fraction is defined as Fd is equal to Cf 1 upon 2 rho V square, and hence tau s is equal to Fd upon A, which is equal to Cf 1 upon 2 rho V square, as AA will get cancelled. Substituting in equation, we will get H is equal to tau s Cp upon V infinity, and H is equal to Cf 1 upon 2 rho V infinity square Cp into Cp upon V infinity. That is Cf divided by 2 H upon rho Cp V infinity, that is nothing but Stanton number. So Stanton number is equal to Cf divided by 2. This equation is known as Reynolds analogy, and this equation is valid when Prandtl number is assumed as 1. So Reynolds analogy assumes Prandtl number is equal to 1, and when Prandtl's number is not equal to 1, poor results are obtained. And this analogy was modified by Chilton and Colburn. And as we know that Nusselt number is equal to 0.664, Reynolds number is to 1 by 2, Prandtl number is to 1 by 3, dividing both sides by Re PR raised to 1 by 3 on both sides. So Nusselt number divided by Re PR raised to 1 by 3, 0.664 Re raised to 1 by 2. So 1 upon 2, 1.328 square root of Re, which is equal to Cf divided by 2. So Nusselt number upon Re into PR raised to 1 by 3, which is equal to Cf by 2. This is Chilton and Colburn analogy, which is further modified as Cf divided by 2 is equal to Stanton into Prandtl number raised to 2 by 3. This is known as Chilton and Colburn analogy, and this equation holds good for Prandtl number ranges from 0.5 to 50, and put Prandtl number is equal to 1 for Reynolds analogy. Thank you very much.